In this example, we're going to take each of the following complex numbers and find 4 properties of them. We will find the real component of the complex number, the imaginary component of the complex number, the modulus of that complex number, as well as the argument theta of that complex number, where the argument will be an angle measure between 0 and 2 pi. We're going to keep all answers exact here, so we should not need a calculator for any part of this. Starting with the first case we have here on the left, we're going to first identify the real and the imaginary component, which should take very little time at all. The real component is the number here that is not multiplying I, that is by itself. So our real component of z is the number -6 square root of 3. Whereas the imaginary component is the number that is multiplying I. We would say the imaginary component, or the imaginary part, I wouldn't say is 6i, it's just the real number that's multiplying I. So it's just 6. Very important that we know that distinction. With those now, we can calculate the modulus. The modulus is the same thing as r when talking about a polar coordinate, and we're going to calculate it the same way, using the Pythagorean theorem. The way that we'll use the Pythagorean theorem is considering the real as x and the imaginary part as y. That means then we're going to take the real component and square that, and then we'll also take the imaginary component and square that. The square root of that result would give me my modulus. So this takes a little bit of work, but -6 square root of 3, that is 36 times 3, so that is 108. Whereas 6 squared, that is just 36. That will give us 144, otherwise known as 12. When calculating r, it is common and it's good practice to consider r to always be the positive. So when talking about the square root here, we're going to take the principal root. So r is, or modulus, is -12. For the argument of z, it is recommended to first, before you even try to calculate that, consider where your complex number would be in the Gauss plane. If I think about this complex number, I have a negative real and a positive imaginary. So that means we'd be going left on the real axis, so that's a negative real. And then we're going up on the imaginary axis, means our complex number is up here in quadrant 2 somewhere. That means the angle measure that I should be getting here is going to be something in quadrant 2. So between pi halves and pi then. The way we are going to calculate theta, however, is the same way that we would calculate theta when talking about taking a rectangular coordinate to a polar coordinate. All we need to use is arctangent of, instead of y over x, the imaginary over the real. So that would be 6 divided by -6 root 3. Now, if we do simplify that, that's arctangent of -1 over root 3. That would mean that I'm looking for an angle measure that would have cosine involving square root of 3, so that would be an angle measure of pi over 6. However, very important note about this. If I'm calculating with arctangent of -1 over root 3, technically arctangent of -1 over root 3 would give me the answer -pi over 6, if we were to calculate that through. But -pi over 6 cannot be my solution because, as we had already said, the complex number should be in quadrant 2, and the angle measure should match that. So, arctangent cannot give me an angle measure between or in quadrant 2, so we would need to adjust our solution here. For example, by adding pi, therefore I'll get the appropriate answer that would be in the correct quadrant. That would give me 5 pi over 6. If my angle measure was already in quadrant 4, then I wouldn't need to do that, but I would need to add 2 pi to get an angle measure between 0 and 2 pi. So keep in mind what function you're using to calculate your angle measure there. Let's put that into action with the second example. In this case, we have -3 minus 4i. Okay, so again, the real component is the value that is not multiplying I. So the real component here is -3, whereas the imaginary component is the number that is multiplying I. So the imaginary component is just -4, not -4i. We can then also calculate the modulus of this complex number. This is again just going to be working with the Pythagorean theorem. And this one in particular is going to be relatively nice. Even more so than the previous one, simply because if we think about what this is creating as a triangle in the appropriate quadrant, this would have a triangle with 2 legs of 3 and 4, meaning what we are working with is a Pythagorean triple. So you can use that concept, or you can calculate it directly to get, in this case, 9 plus 16 underneath the square root, which is square root of 5, or, as we should know from using Pythagorean triples, our third side there is 5. This is a 3, 4, 5 triangle for a complex number. When finding the angle measure, though, again, we need to be careful about this. We need to think about where my complex number would be. If I consider graphing that, I have a negative real, so that puts us left on the negative real axis, and a negative imaginary, so that puts us down on the imaginary axis. So this complex number is down in quadrant 3. Therefore, I would expect an angle measure between pi and 3 pi over 2. If I were to just use arctangent of the imaginary over the real, just like the previous one, so -4 over -3. Well, what that is going to do when I simplify this, arctan of 4 over 3, unlike the previous question, I actually don't recognize that ratio from the unit circle, so I can't simplify that any further. But I do still need to make sure that that's going to give us a correct answer. When we have arctangent of a positive ratio, we should know from knowledge of inverse functions that this is going to give us something between 0 and pi over 2, something in quadrant 1 of the unit circle. But that cannot be correct because, as we have already established, this should be in quadrant 3. So, very similar to the previous question, we need to adjust this. We need to correct the angle measure to not just be arctangent of 4 over 3. We need to add pi to this result. And that would be my angle measure there. Note, we should be able to determine that and write the exact solution of the angle measure in this manner without needing a calculator because of what we know about arctangent. But keep in mind where the complex number should be and make sure that the angle measure you calculate does agree with that.